Hello everyone, my name is Klidos Christodoulou. First of all, my apologies for not being able to be physically attending the conference in Vancouver. I hope that you have a great success with your conference, and please feel free to contact me via email in case that you have any questions or you would like to know more about this work. So this work is about identity discovery and the use of supervised learning in doing so. I will start this presentation by presenting a couple of facts, mainly from the Bitcoin ecosystem. The Bitcoin network provides users, as we know, with the ability not only to transfer financial transactions, but also to publish information that cannot be censored and will be permanently available to the world as long as, of course, the Bitcoin network exists. So there are various ways to store arbitrary data or metadata to the Bitcoin network as long as they follow the protocol specifications. And in this paper, we are focusing in one such method for used for data insertion, and this is the expendable op return code, the op return transactions. So in general, very briefly, op return is a script opcode used to mark a transaction output as invalid. And since, as we described, these transactions are unspendable, so outside the network, such transactions can be used to enable powerful capabilities of the blockchain technology. And this is the first fact that I would like to start to kick off my presentation. So following on that, to understand how the op return looks like, we zoom in a specific transaction. We focus on the list of outputs, and in particular, we observe the op return opcode that is represented by a hex value. That is the hex that starts with OX6A. Followed by the first byte, which represents the length of the rest of the bytes in the script pub key. To decode the message, we need to use a UTF-8 decoder for example, take a look at the highlighted text, and we can decode that highlighted text using a UTF-8 decoder to reveal the information that was injected in that transaction. You can observe this transaction on the Blockchain Explorer yourself. So the second fact that I would like to highlight is that there is an increase on the op return output, the number of op return outputs. Although the Bitcoin community is divided with regards to whether the use of the Bitcoin network as a platform for data publication and storage is appropriate. This is clearly shown of this plot that there is a significant increase on the number of op return output transactions. This definitely shows a huge interest of the community to publish any kind of data or metadata that can be used to enable the new generation of applications on the web. For example, op return can be used for digital asset proof of ownership, and has been used many times to convey any additional information needed to send transactions. So the second fact that I would like to mention is that there is a significant increase of the number of op return output transactions. It is thus expected that even more people will be using the Bitcoin blockchain to store data. And there are a couple of studies that have been published out there, analyzing the types of data that are published on the Bitcoin blockchain. A recent study published by Aachen University in Germany revealed that more than 1,600 files are permanently stored on the Bitcoin blockchain, and it is expected that this number will start growing. From this content, the study showed that there are some legally questionable documents published on the Bitcoin blockchain, and it is evident that the blockchains in general are likely to be leveraged for illegal usage, such as, for example, selling personal data or other illegal activities and threats emerging from the dark web. We still know that Bitcoin itself remains the most popular cryptocurrency for the dark web. So following from that, our study has been motivated by the following questions. Is it possible to investigate the source and destination of suspicious transactions? Is it possible to track transactions that can reveal the identity of the transacting entity? Is it possible to use machine learning algorithms to leverage transactions metadata that can then be used to identify information about the transacting entity, of course based on the available identifiable data? So these three questions have been motivating our research. So observing external data from public addresses, etc., services being used to set up transactions, we can indeed build profiles about the owners of the transacting entities of that Bitcoin addresses. So in a way, yes, we can infer spending patterns, which is one of the ways to reveal personal facts with regards to transacting entities. So following from that, another fact worth mentioning here is that by the nature of the protocol, Bitcoin is pseudonymous and fully traceable. This means that every transaction in the Bitcoin maps inputs to outputs and allowing everyone to follow such transactions. And these transactions are traced and permanently recorded on the blockchain itself. Another fact is that if an entity can elicit this kind of information from the blockchain and links that with identity details from your Bitcoin addresses, etc., then it is likely that they can learn more information about you, about the person or the entity behind that Bitcoin address. So in general, just to sum up, Bitcoin, it is untraceable, but of course there are links there that they can reveal information about the transacting entity are likely to be there. Of course, if we link the information to other external sources, such as details from social media profiles, etc., it is expected that the blockchains will be used for illegal usage, and that was also been proven by the analyzing of data that is already published on the Bitcoin blockchain itself. And it is expected that these illegal activities will continue to grow. So, however, although the characteristics of the Bitcoin blockchain and blockchains in general are quite interesting in terms of their anonymity and the security of the transactions, there are traces on the blockchain that can reveal more information from addresses reusage, from linking transactions with external profiles such as details from social networks. IP addresses reuse when transacting can also reveal leave trace about your identity. And all I'm trying to say here is that if we combine these inputs from multiple transactions, we are likely revealing interesting insights about the entities that are controlling these addresses. Is it possible to use machine learning or other algorithmic approaches to get more insights about the profile of the transacting entity? So our thesis is that data from the Bitcoin blockchain transactions could be leveraged to reveal data insights that could lead to identity discovery. We argue that ownership of arbitrary data and identity discovery can be made possible by observing patterns from the data that are already injected on the Bitcoin blockchain. And we can link such addresses to real entities and reveal more information and useful insights about our identities. So in this paper, we are presenting a methodology for this first experiment on whether we are able to use machine learning or other algorithmic approaches to reveal more insights with regards to transacting entities. We have been using a published dataset that contained approximately 39,000 transactions, and these transactions were issued by 23 different entities. And our purpose is to find a way to extract useful features that will then allow our algorithms, our machine learning algorithms, to capture any patterns in the metadata published on the blockchain, on the Bitcoin blockchain. So we're suggesting a feature vector, and this is used as a bootstrapping phase for our algorithm. And this is what we described on the step 4 of the previous slide, and we are presenting this feature set on table 1. Actually, table 1 is divided in 2 categories, what we refer to as feature set A and feature set B. The computation of those features applies only to non-null op return transactions and content. Both feature sets share 2 features as shown on table 1. For FL, this stands for the length of the op return metadata that is counted in terms of characters. This feature is used based on the assumption that different entities that issue transactions are likely to use op return metadata of different size. From the other hand, we combine this information with FOP as shown on table 1. This is more as a baseline feature since we use the entire content of the op return signature. Finally, from the op return metadata, we create feature vectors, and with regards to this, we then create a set Q as summaries of this respective metadata, and as such, we expect them to exhibit some regularities at the level of character unigrams, which are likely to be able to distinguish the issuing entities. Again, we do this for all the non-null op return transactions, and we construct a feature vector for each. In this work, we cast the problem of identity discovery as a classification problem. For training our classifiers, we have used the dataset previously described, provided by the work of Bartorelli et al. That published some information with regards to this dataset, and an analysis they described in their paper. We used that dataset that was publicly available to train our classifiers from 23 distinct entities. We therefore train our classifiers, and we have created 23 distinct classes for each identity, for each entity, and we have then experimented with various classification models, including naive Bayes, SVMs, random forest, etc. In addition, we also observe algorithms from the deep learning domain, such as the long short-term memory LSTM classification model, which is a special type of a recurrent neural network aimed to tackle the vanishing and exploiting gradient problems which may include occur on the training phase. So we observed the behavior from various classification models. So for our evaluation, we followed a tenfold cross-validation process using the dataset of 39,000 training and testing instances. For evaluation, as the evaluation metric, we used a widely used measurement of measuring the classification accuracy, which is a methodology used for evaluating classification performance. Our figures reported in the paper are presenting the results from the average classification accuracy and the scores achieved from each algorithm. We had two baselines. The first baseline, what we describe as no model. This scheme assumes that no model exists, and we always assign it to the transaction under classification, the most frequent entity. So the second baseline, unlike the first one, here our trainable model employs only the FOP feature that considers the entire content and metadata that is injected on the op return transaction. We had observed some significant and encouraging evaluation results with regards to our feature extraction method. So the evaluation results from the first feature, mainly from the op returns, leading characters shown in table 1 previously and reported now in table 3. In terms of the average classification accuracy, I would like to mention here that for these results, for table 3 and table 4, we are focusing on naive Bayes classifiers. And we run our experiments using a tenfold cross-validation. We are reporting a significant discrimination power of our feature 4 used for this classification task. From the other hand, table 4 includes again the average classification accuracy for our second feature set. Again, but this time we're reporting the accuracy using feature 4 with other machine learning algorithms. Briefly, our conclusions is that with this paper, we managed to leverage data revealed from op return transactions in order to reveal the identity of the transacting entity, assuming that this transacting entity has used the same address and used information on the op return string content that revealed information with regards to that entity. In this work, we assume that this transacting entity. Briefly, in concluding this presentation, in this paper, we leverage data revealed from op-return transactions in order to reveal the identity of the transacting entity by training a series of classifiers. In this work, we assume that these transacting entities have somehow revealed their identities in the past by issuing transactions revealing information with regards to their identity, and therefore we were able to identify patterns from the same transacting entities and train our classifiers with high accuracy. We also contributed a simple but yet powerful feature extraction methodology that is proven to have a great discrimination power. Of course, machine learning itself does not solve all challenges to be used, and we argue that these algorithms need to be used in combination with other sources of intelligence, such as human intelligence, or also associated with other information that are publicly available out there, such as information from social network profiles, etc. For future work, we aim to exploit information leakage resulting from correlating public profiles of online social network users with Bitcoin transactions, and by studying the transactions associated with these addresses to measure whether we can reveal information and collect sensitive data with regards to the transacting entities. That data could be used for preventing crime, for preventing illegal activities on the Bitcoin blockchain. Having said that, I would like to conclude this presentation for our paper, Identity and Discovery in Bitcoin Blockchain, Leveraging Transactions Metadata via Supervised Learning. This research was partially funded from the European Union Horizon 2020 Research and Innovation Program. Please do not hesitate to contact me in case that you have any questions, or whether you would like to discuss and learn more about our research. Thank you very much, and I hope that you enjoy the conference and that you have great success with your research. Thank you very much.